Hello dear students. So we will continue our discussion on various aspects of plasma physics. So far we have seen if we consider plasma as a single particle, how the plasma will be affected by various different types of magnetic and electric fields. So the idea was to keep it simple. Let's say we considered electric field which is homogeneous and static in nature. That means the field is not changing with respect to time and the field is also not changing with respect to space. So we realized that the particle will be accelerated along the direction of the electric field, right. When we changed from the electric field to the magnetic field was taken to be homogeneous, that is uniform with respect to space, and static. So magnetic field is not changing with respect to time. Then we realized that the particle will execute a simple harmonic motion or a circular motion to be precise, and this particle will keep on moving in a circular motion. If there is no additional component of velocity which is parallel to the magnetic field, the particle will execute a circular motion. If there is a component of velocity which is parallel to the magnetic field, the particle will move in a helical path. Now, the most important thing that we should remember from this discussion is that the particle's velocity which is parallel will not be influenced by the magnetic field. Right. So, this was a uniform electric field and a uniform magnetic field. Now, we combined these two uniform magnetic and electric fields and we realized that if this is the case, then a charged particle with a mass and a charge, when experiences perpendicular E and B fields, it will experience the guiding center drift, which we called as the E cross B drift. We derived a relation for the E cross B drift as VE is equals to E cross B by B square, right. So, this is the drift velocity that the guiding center experiences due to the electric and magnetic fields, perpendicular in nature, right. So, this was the story about homogeneous magnetic fields and electric fields. Now, what will happen if there is an inhomogeneity? Inhomogeneity can be in terms of, let us say, space or in time. A simple example could be if the field is changing as the particle is moving, if the magnitude of the field is changing as the particle is moving, or if the magnitude of field is changing in time as the particle is moving. So, it means at each and every point as the particle travels, it experiences different magnitudes of fields. So, this is the inhomogeneous magnetic field. So, for a couple of lectures from now, we will see how the plasma will behave in the presence of non-homogeneous or inhomogeneous electric and magnetic fields. So, our discussion is about non-homogeneous fields. So, for example, in today's class, we will try to understand what is called as the gradient drift and the curvature drift. So, the basic idea is as long as the magnetic field or the electric field is homogeneous, that means it is not changing with respect to space. So, let us say dou B by dou x or dou y or dou z is 0, or the electric field for that matter, and if you keep the magnetic field strength constant with respect to time again. In these cases, the behavior of plasma or the mathematical approach to understand the plasma behavior was simple enough. But the moment you introduce inhomogeneity into the picture, things will become complicated. That means the motion of the particle will not be as simple as circular motion, rather it will be much more complicated. So, what we have to do is we have to understand how we can incorporate the inhomogeneity into the plasma motion, right. Now, so in order to approximate things, we start with introducing what is called as the length or the scale of inhomogeneity. So, what does it mean? The scale of inhomogeneity is the distance after which the magnetic field becomes inhomogeneous. So, let us say we define the scale of inhomogeneity as, let us say, capital L. What it means physically is that up to the length scale of capital L, the magnetic field can be assumed to be homogeneous. And once you cross this limit capital L, the magnetic field will become inhomogeneous. Right. Now, how do we put it in terms of particles properties? How does the scale of inhomogeneity matter when you compare some property of the particle? So, what we can do is we can define RL, which is the radius of gyration, which is equal to mv by qb. We have kind of derived this equation, the formula for radius of gyration. So, what is this? So, this is the radius of gyration. So, radius of gyration matters only when you have a magnetic field in place. So, if RL is the radius of gyration, for us to understand or for us to make a simple mathematical treatment, what we can do is we can say that the radius of gyration will be much less than capital L. What does it mean? It means that the scale over which magnetic field becomes inhomogeneous is much larger than the radius of gyration of a particle. It can be an electron or it can be an ion. So, we also know that the particles, the ions being massive particle has a larger radius of gyration. So, it is very easy, very convenient for us to say that radius of gyration should be very, very small in comparison to the scale of inhomogeneity. So, why are we taking the scale of inhomogeneity in such a proportion is that, so let us say if you have a single particle which is gyrating in a magnetic field in, let us say, in one particular direction, then we do not want the magnetic field to become inhomogeneous within this distance, within the distance of radius of gyration. We want at least the magnetic field to be homogeneous at least in the limits of the radius of gyration. That means, as the particle is revolving, the particle should not experience different magnitudes of magnetic field at different points of its trajectory. So, things, it is not a possibility that is ruled out, but rather we want to make things simple. So, we say that the radius of gyration is at least of the orders that within one radius of gyration itself, within one orbit itself, the magnetic field is not changing so much. That is just something we want to keep for the mathematical approach to be simple, right. So, what it means is that that means RL, so somewhere RL by L will be much less than 1. Okay. Now, if what will happen, let us say, so we have to consider a magnetic field which change. So, we need to consider a magnetic field which changes with respect to space coordinates. Magnetic field can also change with respect to the time coordinates, but so our idea is to understand ionosphere as plasma. So, we are equipping ourselves with enough understanding of plasma physics so that we can understand the type of motion that is involved or that happens or that is manifested in ionosphere. Okay, right. So, now let us consider a particular type of magnetic field. So, let us say the coordinate axes are in this direction. So, this is your z axis that is coming out of the page, and this is your x axis and this is your y axis. So, the magnetic field configuration that I will consider is such that it is pointing out of the page or towards you, right. So, what happens is these are the lines, the magnetic field lines that I am drawing. So, magnetic field lines are out of the page. So, the direction of magnetic field is in the positive z direction. So, what is being drawn here is, as you see, the magnetic field strength is increasing in this particular direction. So, what you can say, so the gradient of the magnetic field is pointed in the y direction. So, what is the gradient? Gradient is the maximum rate of increase or change. So, generally it points towards the increasing direction, right. So, the magnetic field gradient is in this direction, del B. Okay. So, this is the gradient of the, so magnetic field, if you want to write magnetic field's coordinates, you can write magnetic field is 0, along x direction there is no magnetic field, Along y direction there is no magnetic field, but only along z direction the magnetic field is existing. So, it is Bz whose strength is changing across the y direction. We have taken simplest types of fields, let us say for example homogeneous static fields, but in nature we do not generally come across homogeneous fields. So, let us say for example if you consider a simple bar magnet, the magnetic field due to this bar magnet will change at each and every point. So, you cannot expect a homogeneous magnetic field to be present around this point, around this bar magnet. So, it may, it may be possible for you to create homogeneous or uniform magnetic field within some space, but generally the nature of magnetic field is such that it is not homogeneous, or it changes always with respect to the space, because somewhere the magnetic field has to be stronger and somewhere the magnetic field has to be weaker. So, it is always like that. Right. So, now we are trying to implement a natural or physically feasible type of magnetic field which is inhomogeneous in nature. So, now the inhomogeneity of course is, let us say if this is the scale of inhomogeneity is this, let us say capital L. So, what it means is that, so as long as you are within this distance capital L, the magnetic field is homogeneous, right. But if you cross the length scale capital L, the magnetic field changes, right. So, we want now a natural consequence. So, what we have seen in the case of a homogeneous magnetic field, what we have seen is that the particle will experience a force which is basically F is equals to m dV by dt is written as q times V cross P, right. Now, with this type of magnetic field, if you resolve this cross product, what you can see is that Fx will be equals to q times Vy B z, Fy is equals to minus q times Vx Bz, and Fz will be 0. So, this has to be in combination with our understanding that V has a component of velocity Vx, Vy and Vz. The Vx and Vy components can be called as the perpendicular components, and Vz component is the parallel component. Now, since Vz is parallel to the magnetic field itself, so the velocity across the z direction will not be altered by the magnetic field. So, there will not be any acceleration that you can see in the direction parallel to the magnetic field. So, that means that magnetic field will not do any work parallel to the parallel direction, right. So, what I am trying to say is this is the velocity of the particle to begin with. If this particle makes an entry into the magnetic field, it will experience a force like this. Now, what we did was, these are two differential equations which are kind of coupled. So, we solved these differential equations and we assumed solutions for the velocity. So, this is m dvx by dt, it is f is m dvx by dt, right. So, then we obtained a solution which implicated that the particle is executing circular motion in the magnetic field, right. Now, if you can use this approximation, or you can use this solution as it is for this picture. How do you use it? What you can say is that you have defined the particle to be executing a simple harmonic motion or circular motion with a radius of gyration which is mv perpendicular by qb. So, if you make plasma to enter into this magnetic field, what you can realize is that the particles at this lower end, at the bottom end, will have the magnetic field strength being lower here, will have a radius of gyration which is larger, and as the particle moves, or if the particle is here, the magnetic field strength is larger here. So, the radius of gyration will become smaller. That means, just it is kind of consistent with our idea of the drift of the guiding centers, which is like we have seen that when the particle is experiencing an E cross B field, we have seen that as the particle travels or tries to gyrate across, then due to the effect of the electric field and in combination with the initial velocity of the particle, the radius of gyration in the first half cycle will not be same as the radius of gyration in the second half cycle. So, because of the change in the radius of gyration, we say that the guiding centers are drifting in a particular direction with a particular velocity, and this guiding center of drift velocity is irrespective of the charge and the mass of the particle, right. So, similarly here also what you are able to see now itself is that the radius of gyration as the particle moves from here to here changes by some magnitude. That means the particle's radius of gyration starts becoming smaller and smaller. So, what does it mean? Due to this radius of gyration changing, we can experience some drift velocity in this direction, drift of the guiding center. Let us say we call this as V del B. Now, why is this drift velocity coming into the picture itself? Has it been a uniform magnetic field? The radius of gyration would have been same all the while. So, there is no idea of the drift velocity. But since there is a drift velocity that is developing due to the radius of gyration being larger at a point and smaller at a point, and this radius of gyration changing is mainly due to the fact that the magnetic field is having a gradient. So, we call this drift velocity as the gradient drift velocity. So, the particle experiences, in this situation, the particle experiences what is called as the gradient drift. Okay. Now, so let us try to derive an expression for the gradient drift velocity, right. Now, what you have to do is we have to find out, we already know if we have a generalized force F, then the drift velocity associated with this is, we have derived this in our earlier class as VE is equals to 1 by Q F cross B by B square. Now, what is the role of this F? This generalized force is able to give a particle with a charge and a mass m some initial velocity. So, this is a generalized expression. Generally, the relation that we have derived is VE is equals to E cross B by B square, right. So, this is the relation that we have derived, and then we made a small modification in this expression, and then we said that the generalized expression. So, you can substitute the force to be an electric force, F is equals to EQ. You can as well substitute F is equals to mg, or you can as well substitute F is equals to mv square by r, anything. But the point is, when the particle is experiencing a generalized force in combination with the magnetic field, the drift velocity will be given by this. So, what is the simplest example? The simplest example is the earth itself. Let us say earth has a magnetic field, due to the magnetic field due to the revolving molten core of iron that is at the center of the earth, due to which a magnetic field is present along with the earth. So, the magnetic field of the earth is something like this. So, the magnetic field lines, let us say magnetic field lines diverge away from the geographic south pole and converge at the geographic north pole. So, this is the geographic north and this is the geographic south, and the geographic north is actually coinciding with the magnetic south, and the geographic south is coinciding with the magnetic north. So, let us say it is N M and S M. Okay. Now, what you see here is that, as let us say if you put a particle at rest, if you are able to do it, if you put a particle at rest, the magnetic field, the particle is able to see the magnetic field, but the particle does not have its initial velocity, but the particle certainly has some mass. But so, it will experience a force mg towards the earth, and this force gives it an initial velocity, then the magnetic field will take over, and there, as the particle travels closer and closer to the earth, the magnetic field strength becomes larger, becomes strong. So, there is a magnetic field gradient which is going towards the earth, and the particle is experiencing some force due to the gravity as well, right. So, this is a realistic example where the plasma or the solar wind that is coming towards the earth will experience some kind of drift due to the gradient in the magnetic field, right. This is one example. So, now what we have to do is, so if the particle is experiencing a magnetic field gradient, we have to calculate what will be the average force that will be experienced by the particle as its radius of gyration decreases along the gradient, right. So, if you know the force, let us say if you calculate the force, you just have to substitute that force into this generalized drift velocity expression, then you will be able to get the original expression for the drift velocity. Okay. Now, so for us to do that, we have to make some approximation. So, since the gradient is present only in the y direction, the magnetic field is along the z direction. So, it is dou Bz, and since the gradient is present only in the y direction, the magnetic field's derivative with respect to other space coordinates does not mean anything. So, this can be approximated to, let us say, Bz over L, since L is the space dimension within which the magnetic field is actually not changing, right. Right. So, this can be equated saying that Bz by L must be much less than Bz by RL, which implies RL times dou Bz by dou y should be much less than Bz itself, right. Now, what we do is we within the limit of this scale distance over which field is homogeneous, we make a Taylor expansion of the magnetic field. So, how do we do it? B0 is the magnetic field strength at the origin, or let us say at the guiding center's coordinate x0, y0, or at origin. So, where the particle is initially present at the origin, the position is x0, y0, and the magnetic field strength is B0. Now, if the magnetic field strength at the guiding center is B0, the magnetic field strength at a distance r can be approximated by Taylor series expansion, which is equals to, so which is B0 plus r dot del times B naught. Now, what are we trying to do? We are trying to see B0 is the magnetic field strength at the origin or at the center of the radius of gyration, or at the center of orbit of gyration, right. So, that means, so we have to find out what will be the magnetic field. Now, the magnetic field is not uniform. So, the magnetic field has to be calculated at any distance r away from the center. Do you know the magnetic field strength at the center? Yes, we know the magnetic field at the center to be equal to B naught. Now, if you know the B naught, then at any distance r, knowing how much B changes over distance r, we can find out what is the magnetic field at any point. So, this point is at r. Okay. So, again, so this is a very familiar form of the Taylor series. So, what we can do is we can expand it, saying that B0 plus y times dou B by dou y plus the higher order terms. Okay. So, mathematically we do not deal with the higher order terms, we say that the higher order terms are too small to be considered in calculation. So, we ignore them. So, we will take only the first two terms in our calculation. So, what are we trying to do is we are again trying to find out or calculate the expressions for Fx, Fy and Fz. Okay. Now, just to recollect, so we have in the case of a uniform static magnetic field, we have seen that if the particle experiences a magnetic field which is uniform in space, we have seen that x is equals to RL sin omega c t and y is equals to plus minus RL cos omega c t, which gives you kind of Vx is equals to V perpendicular cos omega c t and Vy is equals to plus minus V perpendicular sin omega c t. Now, this plus minus indicate the direction in which the particle will gyrate, some to the left and some to the right, right. So, this is we know this already, right. So, now if you want to substitute this into the expressions for Fx and Fy, we know that Fx is q Vy B z, right. Now, if you substitute q V perpendicular sin omega c t times Bz at a distance r is Taylor expansion of Bz plus minus RL cos omega c t into dou Bz by dou y. Similarly, we can write Fy as minus qVx Bz, which is equals to minus q V perpendicular cos omega c t times B naught plus minus RL cos omega C t dou B by dou y, right. And what is Fz? Fz is 0 and Fz is anyway 0, right. Now, what is different here in comparison to what we have done earlier? The difference is that the particle is experiencing this force. Earlier the particle was experiencing this force just because of the magnetic field Bz. There was no substitution for Bz. Right now we are substituting something for Bz. That means what is the force that is experienced by the particle as by the virtue of the magnetic field. Now, since the magnetic field is not constant, but it is changing with respect to space, this variation with respect to space. So, the magnetic field is constant at the guiding center. You know the magnetic field at the guiding center. You know, you want to find out what will be the magnetic field at a distance r, not at a distance of RL, but at a distance r. So, then if this magnetic field is changing, so you have this original term. This original term is q v perpendicular B naught sin omega C t is still there. In addition to that, you also have a second term which has come into picture only because of the gradient in the magnetic field, right. Now, because of this, so Fx, Fy and Fz are the magnitudes of forces which are experienced by the particle. Now, what you want to do is, at this point, we want to find out what is the average force the particle experiences over one gyro orbit, that means 0 to 2 pi. So, between 0 to 2 pi within one gyro orbit, let us say within one gyro orbit, what is the average force? What is the average value of Fx? What is the average value of Fy? And what is the average value of Fz? So, the point is, you want to find out what are the average forces the particle will experience within one gyro orbit. Then we can probably use it to calculate our drift velocity. So, the average of Fz is anyway 0. Average of Fx, if you want to calculate, will be q v perpendicular times B naught average of sin omega C t plus minus RL sin omega C t cos omega C t into dou Bz by dou y. We know that average of sin omega C t in a full cycle is 0 and average of sin omega C t times cos omega C t, which is half sin 2 omega C t, is again 0, right. So, that means that the average force in the x direction is 0. So, the particle is not experiencing any force due to the change or due to the gradient in the magnetic field in the x direction, which is natural, which is kind of expected already, right. And we also know that Fz is also 0, the average Fz is also 0. Now, let us find out if there will be an average force across the y direction. Okay. Across the y direction, it will be minus q v perpendicular B naught cos omega C t plus minus RL cos square omega C t dou B dou y. Right. Now, the average of cos omega C t is 0, of course, over the full circle, and the average of cos square omega C t is half. So, the average force Fy will now become minus q v perpendicular plus minus RL cos square omega C t dou Bz by dou y, which is equals to minus plus q v perpendicular RL divided by 2 dou Bz by dou y. So, the average force along x direction is calculated to be 0, the average force along the y direction is calculated to be this, and the average force along the z direction is also calculated to be 0, right. Now, so we have calculated Fx, Fy and Fz. So, we can use these three in the expression for the generalized drift velocity as 1 by q F cross B by B square. Okay. So, we will stop here. Then in the next class, we will try to see how we can substitute this into the drift velocity formula and how we can get the gradient drift velocity and what are the consequences of such a drift velocity. So, from here what we can see is that if the particle is experiencing a magnetic field which is changing with respect to space, it will we have been able to calculate three different components of the forces. The force, mainly the origin is again the Lorentzian force. We have been able to calculate Fx, Fy and Fz. Some of them are 0 already, right. But so we will see how now what we are trying to achieve is that we know the force. Once we know the force, we have a generalized expression for the drift velocity in terms of the force and the magnetic field. We can use this expression. We can use this expression to calculate the generalized drift velocity in the presence of a. So, this should be 1 by q F cross B by B square. So, where F is the generalized force. Now, let us see how we can utilize these components, the average components of the force that we have derived and then substitute into this equation, and let us see how it will give us the drift velocity. Okay.